Welcome back. The uniqueness quantifier. There are other quantifiers such as there exists at least two or there exists exactly three and so on. Among these quantifiers, the uniqueness quantifier denoted there exists unique or there exists exactly one is most often seen. The notations there exists x, unique x, px, or there exists exactly one x, px, stands for there exists a unique x such that px. For example, there exists unique x minus 2 is a true quantification. Quantifiers with restricted domains. An abbreviated notation is often used to restrict the domain of a quantifier. The condition a variable must satisfy is included after the quantifier. For example, for all x less than 0, x cube is less than 0. Is this true? Yes, this is true. For every x that is less than 0, its third power is less than 0. Compare with for every x less than 0 implies x cube less than 0. Okay. Likewise, for all y non-zero, y squared is less than 0. Is this true? No, it is not true. For instance, all you need is any y that's not 0. Its square is definitely not less than 0. Well, this may also be rewritten as for every y not 0 implies y squared less than 0. Here is an existence quantifier. There exists z greater than 0 such that z squared is 5. Is this true? Yes, there exists z. And that z is square root 5, by the way. Square of square root 5 is 5. Compare with there exists z greater than 0 and z squared equals 5. So this may be rewritten in this fashion. Precedence of quantifiers. The quantifiers, not the quantifiers for all and their exists have higher precedence than all the logical operators from propositional calculus. For example, for every xpx or qx, what does this mean? It means the disjunction of qx with the uh, the quantifier for all x px. Likewise, there exists x rx and sx means it's a conjunction of sx and the proposition there exists x rx. Okay. Binding variables. When a quantifier is used on the variable x, we say that this occurrence of the variable is bound. An occurrence of a variable that is not bound by a quantifier or set equal to a particular value is said to be free. For example, for all x plus y equals 3, the variable x is bound by the quantifier for all, while the variable y is free. Okay? All the variables that occur in a propositional function must be bound or set equal to a particular value to turn it into a proposition. This can be done using a combination of universal quantifiers, existential quantifiers, and value assignments. The part of a logical expression to which a quantifier is applied is called the scope of this quantifier. Consequently, a variable is free if it is outside the scope of all quantifiers in the formula that specify this variable. So, to be free is to be not bound. Okay? So, the part of a logical expression to which a quantifier is applied is called the scope. A variable is free if it is outside the scope of all quantifiers. Okay. For consider the statement for all x, px or qx. Okay, so this proposition is uh, for all x. X is bound by this quantifier x for all, whereas y is bound by this quantifier existence. So there are only two variables, x and y. All variables are bound. The scope of for all x is just this expression, px or qx. So y doesn't show up here. The scope of there exists y is the expression ry. Note, in common usage though, the two variables were unnecessary since the scopes do not overlap. So instead of writing in this fashion, you may have as well written as for all x, px or qx, and, right, there exists x, rx, such that rx. So you didn't need these two different variables. Logical equivalences involving quantifiers. Definition. Statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value, no matter which predicates are substituted into these statements. Which domain of discourse is used for the variables in this propositional functions. We use the notation S equivalent to T to indicate that the two statements S and T involving predicates and quantifiers are logically equivalent. Show that for all x, px and qx. So this is a proposition for all x, px and for all x, qx. So you notice what this says is for all x, px and qx. That is, for every x, px holds true and qx holds true. This may be rewritten as for every x, px holds true and for every x, qx holds true. They are logically equivalent. Determine whether for all x, px, if and only qx, and for all x, px, if and only for all x, qx are logically equivalent.